Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on ring theory, lecture number 17, in which I will prove some more theorems on field. Now we will prove a theorem. Theorem is a finite integral domain is a field. Let D be a finite integral domain containing n elements a0, a1, a2, a n minus 1, in which a0 be the zero element. Since D is an integral domain, therefore number 1, D is a ring. Number 2, having unity. Number 3, commutative. Number 4, having no divisor of 0. Let A1 is not unity in D, and let us consider the products A1 multiply A1, comma, A1 multiply A2, comma, A1 multiply A3, comma, comma, A1 multiply AN minus 1. Since D is a ring, so it fulfills closure property with respect to multiplication. Therefore, all these elements belong to D, and these are A1, A2, AN minus 1 are non-zero, and since D contains no divisor of 0, therefore A1 multiply AI not equal to 0 for I 1, 2, 3, n minus 1. If possible, let A1 multiply AI equal to A1 multiply AJ. I lies between 1 and n minus 1. J lies between 1 and n minus 1. And I not equal to J. From this we get A1 multiply AI minus A1 multiply AJ equal to 0. Since D is a ring, so it is distributive. Here, this means A1 multiply under bracket AI minus AJ. Since D contains no divisor of 0, therefore A1 is not 0 element, hence AI minus AJ equal to 0 implies that AI equal to AJ. But here we have taken that I not equal to J, that means AI not equal to AJ implies that A1 multiply AI not equal to A1 multiply AJ. Thus, the elements A1 multiply A1, comma, A1 multiply A2, comma, A1 multiply AN minus 1, all are n minus 1 distinct non-zero elements of D in some order. Since D contains unity, so one of these elements must be unity in D. Let A1 multiply AP equal to unity I. Since D is commutative, therefore A1 multiply AP equal to AP multiply A1 equal to unity. This proves that AP be the inverse of A1. That means A1 is a unit in D. Similarly, we may show that each non-zero element of D is a unit. So here we get that D is a ring, D contains unity element, D is commutative, and each non-zero element of D is a unit. Therefore, D is a field. Proved. Now we prove the next theorem. Theorem is a non-trivial finite commutative ring having no divisor of 0 is a field. Let R be a ring. Given that R is non-trivial and finite, this is number 1. Number 2, R is commutative. Number 3, R contains no divisor of 0. Since we know that every non-trivial finite ring having no divisor of 0 is a ring with unity, here we see that R is non-trivial and finite and having no divisor of 0. Therefore, this R contains unity. This is number 4. From 1, 2, 3, 4, we get that R is non-trivial and finite ring. Number 2, it is commutative. Number 3, having no divisor of 0. Number 4, R contains unity. Therefore, R is an integral domain. Since this integral domain is finite, we know that every finite integral domain is a field. Therefore, R is a field. Proved. Now we prove the next theorem. Theorem is a non-trivial finite ring containing no divisor of 0 is a skew field. Now we prove this. Prove. Let R be a ring. Then number 1, R is non-trivial and finite. Number 2, R contains no divisor of 0. Since we know that every non-trivial finite ring having no divisor of 0 is a ring with unity. Therefore, this R contains unity. This is number 3. Again, we know that every non-zero element in a finite ring having no divisor of 0 is unit. Since R is a finite ring and contains no divisor of 0, therefore each non-zero element of R is a unit. This is number 4. Therefore, from 1, in 1, R is a non-trivial finite ring. Number 3, R contains unity. Number 4, each non-zero element of R is unit. Then R is a skew field. Proved. Now we prove the next theorem. Theorem is the characteristic of a field is either 0 or a prime number. Since we know that a field is an integral domain, and also we know that characteristic of an integral domain is either 0 or a prime number. Therefore, F is a field, implies that F is an integral domain, implies that the characteristic of f is either 0 or a prime number. That is, the characteristic of the field f is either 0 or a prime number. Proved. Now we prove the next theorem. Next theorem is, if p is a prime number, then prove that Zp with binary composition, addition and multiplication is a field with characteristic p. Now we prove this. Since we know that Zp with binary composition, addition and multiplication is a finite integral domain. Since every finite integral domain is a field, we know this. Therefore, Zp with binary composition, addition and multiplication is a finite field. Let this is number 1. Again, we know that the characteristic of an integral domain is either 0 or a prime number. Here, the characteristic of integral domain Zp with binary composition, addition and multiplication is the prime number p. Implies that characteristic of the finite field Zp with binary composition, addition and multiplication is p. This is number 2. From 1 and 2 we get that Zp with binary composition, addition and multiplication is a finite field with characteristic p. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.